Hello, everyone. This is Halim Yanikomeroglu at Carleton University, Canada. And today is May 31st, 2022. One reason why I wanted to say the date is that the area is moving forward quite fast. And I will be making some predictions about the future of wireless. It is important that we know when these things are said. Well, here is the title of my presentation. And even before that, the plan is to have a 1-hour presentation and followed by discussion in the second hour for with those of you who can stay. The title is quite mouthful: Integrated Terrestrial-HAPS-Satellite Networks of the Future Towards a Sustainable ICT Ecosystem. I would like to unpack a number of phrases here. Well, terrestrial network, I'm sure we are all familiar with. It is the legacy part of this story. Satellite network, there is a big excitement about that. It can be considered as an emerging framework. However, it is worth remarking that it has indeed rich history. Commercial communications with satellites is a reality for the last few decades indeed. There is a rejuvenation in this area with mega constellations. Just a couple of years ago, when the community started hearing about Starlink, people were very puzzled, amazed. There is this startup company got permission to put up several thousand satellites, perhaps up to tens of thousands of satellites in the future. And at the time, and this is just a couple of years ago, literally, because SpaceX Starlink put up its first satellite, I believe, in 2019. So in 2018, people like me who are coming from the terrestrial networks background had very limited knowledge about satellite networks. Therefore, whatever you say would be very interesting at the time. However, the community has been exposed to the potentials of and the fundamental dynamics of satellite networks substantially in the last few years. Therefore, most people have the basic understanding of satellite networks. On the other hand, that's not the case for high-altitude platform stations. The dynamics as well as potentials are not well understood. As such, in today's presentation, although the framework is this integrated terrestrial HAPS-Satellite network, I will mainly focus on HAPS with a goal to understand it is better understand its dynamics and try to envision its potentials which go well beyond connectivity. I will just put up a couple of slides early on for those of you who are not that familiar with HAPS, although people in my group are very familiar. HAPS is some sort of an aircraft in stratosphere, which is at a fixed point with respect to ground. That is, it is not orbiting. It is, in our vision, this is a type of base station integrated with the terrestrial network. Actually, to the extent that even integration is a bit of a limiting term, we envision it really part of the terrestrial network. It will be a bit of abuse of the terminology. It is in stratosphere, but really it is part of the terrestrial network from architecture viewpoint. Therefore, we have a 3-tier network with small base stations, macro base stations, and super macro base stations. I think it was our group which coined this term super macro base station in a communications magazine paper published last year. And after 1 year, I see the term being used by others as well. Now, on one hand, this base station is up in the air. To be more precise, it is in stratosphere. But on the other hand, it is not that far away either. I would like to remind that LTE control channel allows a cell size of about 14 kilometers without any modification. And if there is some modification, the cell size can be much larger. Basically, what I am saying is that the distance from HAPS to a ground user is not too different than the high-end distance in an LTE network. There is, of course, a lot to say about HAPS. It might come in different forms. Here, this is an artist's rendition in the form of an airship, a blimp, something like Zeppelin, if you know this word from the first half of the last century. But it might be in the form of a glider or unmanned airplane. I have given many talks on high altitude platform systems, and I don't want this to be a repeat. Therefore, I will not resort to the slides I have used in my other presentations that you might be familiar with, except for a few slides like this one. As a matter of fact, this one was the last slide in a former presentation. I am just putting it as the first slide in this presentation to put the framework, which is obviously not something that can happen from today to tomorrow. It is a long-term vision. But at some point in time, in a metro area, whether it is GTA, Greater Toronto Area, or even a bigger metropolitan area such as Istanbul with almost 20 million population, in the skies, we can have a number of high altitude platform base stations, which are quote unquote connected to each other with super high speed free space optical links. And then this cluster, say on top of Toronto, can be connected to another cluster in say Detroit and Syracuse, and also connected to the satellite network, in particular the LEO network. This cluster of HAPS nodes can form a distributed massive antenna architectures with very high number of beams for a variety of use cases. Some of those beams might be pencil beam. In my earlier presentations, I made some back of the envelope calculations. For instance, a beam width of 0.2 degrees at 20 kilometers can create a hotspot of diameter 70 meters on the ground. In some other cases, it is we might choose to have a very broad beam for IoT type of applications, and so on. This is good for terrestrial users, backhauling small cells, aerial highways for drones in the future. Basically, the type of applications are very, very many. The air interface with the ground users can be 5G, 6G, and when the time comes, 7G. Once you have this big infrastructure, it can be utilized for purposes beyond communications. For instance, for edge intelligence, computing, sensing, navigation, and so on. So we are indeed talking much more than access only. This is an entire infrastructure with access, backhauling, edge intelligence, again, transport network, core network, spectrum, and FSO. And at some point, globally, we might have tens of thousands of HAPS nodes. The number seems to be very high, but our community is already talking about a total of more than 100,000 LEO satellites by 2030. So it may not be that outrageous to think of having HAPS on top of pretty much every urban and suburban community. And as I will argue later in my presentation, this framework is truly transformative as it can be. Once again, I don't want this presentation to be overlapping too much with my earlier presentations, in which I covered many topics which are captured in quite a number of concept and vision papers our group published with our collaborators last year in 2021. I already mentioned this first communications magazine paper, high altitude platform station-based super macro base station constellations. In today's presentation, actually, I will highlight later some of the findings in the second paper and papers in this sequel, aerial platforms with reconfigurable smart surfaces for 5G and beyond. The third paper is arguably the most comprehensive paper in literature with, I believe, 52 pages, a vision and framework for HAPS networks of the future. We also published in the management of this multi-tier architecture, which we call a vertical heterogeneous network. We also have a number of magazine papers, at least two as shown here, on HAPS as a facilitator for aerial highways and retail industry delivery networks and applications of that sort. Those ideas are captured in the third last and second last papers. And the last paper is under, I believe, a final stage of the review process. This is on HAPS-enabled intelligent transportation systems, giving service to transcontinental highways, whether it is Trans-Siberian Highway, Trans-Canada Highway, and this paper actually investigates a Trans-Africa Highway, which is an interesting piece. But as I said, I don't want to go into most of those topics today. Here is my YouTube channel. There are a number of presentations there. I will also put up this presentation in the YouTube channel as well. Before I forget, I gratefully acknowledge my team members, junior ones and senior ones, as well as my collaborators in academia and industry. These ideas are not my thoughts from over the last weekend, but literally years and years of brainstorming with many talented people. Once again, I feel privileged for the opportunity to work with them. In today's presentation, I will highlight an aspect which I haven't highlighted much in previous presentations, and that is the sustainability, a sustainable ICT ecosystem, information and communication technologies. In the unpacking process, the final word is future. Here is a slide from 3GPP website. Release 17 was out a few months ago. As you know, currently release 18 work is progressing at full speed. This is a 5G advanced. And already there is a rough timeline for release 17, and 3GPP community is putting together the agenda items for release 19. My expectation is that release 20 will be similar to release 14, which was between 4G and 5G. And then release 21 may well be the first 6G standard similar to release 15. Well, what I am trying to say is that 6G standardization will start very soon, just in 3 years' time, or even 2.5 years, which is around the corner. And then we will see 6G deployments throughout next decade. But in particular, from standardization point of view, 6G is too close for any major infrastructural or architectural upgrades. Therefore, this discussion inevitably will have to have a longer time frame. When we talk about infrastructure and architecture, we are talking about not a component of the network, but the entire network. It's a big discussion with many elements, some of which are indeed regulation related, and regulation you have to go to, for instance, for spectrum ITU, a very slowly evolving process. And then infrastructure requires tens of billions of dollars of investment. Anyhow, just this is the way it is. Things happen not very quickly. Let us keep that in mind. Otherwise, you know, we talk about HAPS, and then a few years later, someone watching this video shouldn't say that, hey, in 2022, you were predicting about future HAPS applications. It is already 2027. You know, nothing much happened. Well, again, I have a much longer vision in mind due to the reasons I have just mentioned. And finally, there is a lot of NTN discussion going on in 3GPP circles. NTN stands for non-terrestrial networks. What it means is an integrated terrestrial satellite, in particular LEO network. At the moment, HAPS is not a focus point in 3GPP. Already it is there in documents as a placeholder. Well, you know, this NTN discussion, sorry, is a big discussion that I don't want to get into from satellite's viewpoint at the moment. But let us keep in mind that in the current 6G context, NTN discussion, by the way, NTN discussion will continue beyond 6G, obviously. But at the moment, there are two major classes of applications. One class is backhauling, backhauling of some remote and rural base stations, or backhauling of a moving vehicle such as a train or a bus, or low rate applications if we are talking about direct to device connectivity, IoT. So those applications, you know, just spread in a large area in which infrastructure may not be present in a dense form, and each device requires very low rates like fire detection sensors. It is a very good application for LEOs in particular. But 6G NTN discussion does not include direct connection to a smartphone when we have high-end applications like video streaming. So in the next several years, I believe the community will have a lot of knowledge gathered in this area. And in the 6G plus era, the best practices will be utilized for terrestrial HAPS, HAPS-LEO, and then all three terrestrial HAPS-LEO integration. I'm already 20 minutes into the presentation, but here is agenda for the rest of the presentation. I will give some highlights of high altitude platform station systems. Then I will open a big parenthesis and talk about transformative research and present my views whether rate increase can be classified as transformative or not. Then some discussion on sustainability, and then a little bit more technical discussion on the synergy between HAPS and reconfigurable intelligent surfaces, that is HAPS-mounted RIS, and then some final thoughts before the floor will be open for discussions. HAPS has a long history in ITU, but as an aerospace topic, as an aircraft, it has a much longer history. Actually, airships predates planes, going back to late 19th century. There are not many of them today because I believe there is no need for transportation purposes. Of course, planes have big advantages. So what I am trying to say is that although this picture you see is again an artist's rendition looking for a futuristic aircraft, but indeed airships do exist for a very long time. Getting back to ITU's interest is due to remote and rural coverage. It was clear to radio engineers from early on that it would be difficult to have terrestrial infrastructure in places where population density is low due to just economic reasons. So satellites and then HAPS systems are considered for those applications. ITU has been dedicating generously spectrum for these applications for the last 25 years. However, I would like to remark that this rural and remote focus is a double-edged sword. On the downside, it makes the economical feasibility questionable. It's a small market, it goes without saying. What is new in the game is that for the last few years and in the next coming years, we will have more and more LEO mega constellations for this market. Therefore, HAPS in rural and remote is becoming more and more difficult in my view. Our vision is different than ITU vision. We are considering first and foremost urban connectivity. And when ITU dedicated spectrum, as I mentioned in the previous slide, this was dedicated spectrum like satellites, meaning that separate spectrum than the terrestrial networks, meaning that you would need a different air interface and you would need a different device. And no one really wants to carry multiple devices. That was another stopper for the advent of HAPS systems. The reason is obvious. HAPS, similar to satellites, can create an interference shower in a very large footprint, and this is a big concern for terrestrial operators. So for that reason, from the beginning in ITU, this was a separate discussion than terrestrial networks. However, as I mentioned, we are talking about a network integrated with the terrestrial network. So it has one air interface, one device, one network. I should actually mention that ITU's viewpoint is also evolving. And there was a big placeholder back in World Radio Conference 1999. A study item is placed in World Radio Conference 2023 agenda for harmonized spectrum below 2.7 gigahertz. So this document is from ITUR Working Party 5D, which means really IMT networks, that is the terrestrial networks. Meeting number 49 that I attended with some researchers from my group, I believe Dr. Omid Abbasi and Dr. Animesh Yadav. And ITU is considering harmonized spectrum for the very first time in its history of, in the HAPS context, for quote unquote integrated, I will just unpack that integrated in this context, terrestrial HAPS operations. Just a word here I will use in the next few slides, but not later. In ITU, when the term HAPS is used, it is reserved for a standalone network in rural and remote communities. But when we are talking about HAPS as a base station working with an IMT air interface, like a 5G, 6G air interface, it is called HAPS as an IMT base station, HIPS. And in the mobile service in certain frequency bands below 7 gigahertz, meaning that with same device, you can connect to terrestrial network or a HIPS, but not both of them. I'll just come to that in a moment. What happened recently, which is quite an exciting development, in this meeting number 39 back in October 2021, we as the Carleton University, through World Wireless Research Forum, WWRF, made a proposal which got accepted after quite a bit of discussion. And that is this actually blurb, as you read at the end of the slide, in addition to the legacy rural and remote connectivity, and in addition to harmonized spectrum less than 2.7 gigahertz, as well as supporting and complementing the terrestrial network in urban areas. This is a first, it is a placeholder at the moment. In the most recent Working Party 5D meeting, which was held in, I believe, February 2022, meeting number 40, the placeholder stayed as is. Our hope is that this will be there in World Radio Conference 2023 documents, and eventually it will become a study item for a meeting in 2027. Just to explain this in a better way, so in ITU, when the term HAPS used, it means an HAPS only network with no integration. There is no terrestrial network. We are in rural and remote coverage. So these devices on the ground are connected to an aerial base station. So the new scenario in 2023 is, again, quote unquote, integrated HAPS, HIPS, I should say, that's an important distinction, HIPS terrestrial macro base station operation. But it should be noted that there is no overlapping or intentional overlapping in the coverage regions. So this is, say, Ottawa. Ottawa is covered by the terrestrial network, macro base stations. But when you go outside Ottawa, let us say 50 kilometers away to your cottage, that area does not have terrestrial coverage. Your same device is connected to HAPS. But what happens is that this HAPS footprint inevitably will have leakage to the terrestrial area, meaning that while this beam is shooting to this user terminal, it will create interference in the urban area to terminals which are connected to macro base stations. What we are proposing, so therefore really integration is in a very light sense, meaning that we have the same air interface, same device, but no overlapping coverage region. And here is the proposed scenario, which is the real integrated HAPS terrestrial network, the same area, again, Ottawa, is served by HAPS and terrestrial infrastructure. As you see now, we have a very rich, interference situation. The footprint of HAPS might affect 100 macro base stations. So it is different than the conventional interference situation we are used to in terrestrial networks, in which a few neighboring base stations might be interacting with each other. But in this case, HAPS interacts with a very large number of base stations, and their distance are not very different to HAPS. So this one is 20 kilometers, maybe this one is 40 kilometers away. The path loss is rather similar. And if we are thinking about downlink once again, as this user here served by HAPS, it will be picking up interference from this macro base station, which is serving a terrestrial base station. And eventually, we might have even a richer system with small base stations as well. That is the three-tier architecture we were talking about. I guess the discussions in ITU meetings are confidential to some extent, but I can remark that while some operators were and are very supportive of this new vision, that is HAPS serving rural, not urban communities as a helper, supporter of the terrestrial network, some other operators are quite nervous, and I understand that very well, because the interference situation has to be sorted out. So if anyone is looking for a research topic for HAPS systems or integrated HAPS terrestrial networks, it's really interference. Currently, it is a big showstopper. Interference is very significant. We have to develop ways to assure the community that it can work. Let us move on. I'm just changing the discussion to a very different angle, and that is transformative research. We have been hearing this word very often recently, especially in the funding agencies. NSF was the first, as far as I know, which brought this transformative research definition. Other than incremental research, basically, in a nutshell, it has to be radically different. Answer definition for transformational is as follows. Something transformational should have the potential to create a significant and real change or impact, a noticeable leap or tangible breakthrough rather than incremental advance. So overwhelming majority of research we do is incremental, again, inevitably, and I am not saying that in any dismissive manner. If we are talking about a $10 trillion ecosystem, even the most minute change, as long as there is some changeable increment, means a lot. That goes without saying. Most of our research is incremental. Most of my research is incremental. There is nothing to be shy about that. However, transformational is really another category. And this impact is, in my view, a key term. But that may mean different things to the research community and to the end user. For instance, a new set of analytical tools which might enable us doing legacy things in a much elegant way might be transformative. You don't invent new mathematics that often, as you know. But what does that mean to the end user? You know, take a lay user the smartphone means for the lay user calling an Uber or having FaceTime. So the end user might say, okay, I'm having FaceTime. It is really transformative. I just give an example. When I came to Canada as a graduate student back in 1990 to University of Toronto, there was, of course, no internet. There was no mobile phone, at least accessible to me. And just to call my parents, the tariff from landline, and even that was not affordable. Friday night after midnight, it was a cheap tariff. And I used to go across my residence right at the corner of Bloor and St. George streets at U of T campus. There was a phone booth on the street, and it only accepted quarters. So the routine was throughout the week, you collect quarters, like 30 of them. And then the first minute was cheap, and then it, I guess, became quite expensive. So you put, I don't know, 10 of them, 12 of those coins quickly and say in 59 seconds, no worries, I am doing good, and a very quick summary of the week. Today, it is free. You can do FaceTime with anyone, anywhere. Isn't that transformative? 30 plus years later, I feel much more connected to my friends and family members in Turkey in comparison to 30 years ago. Whether they live in Toronto or in Ankara is no difference due to FaceTime. It is transformative. Now, but you say that, hey, I invent this big mathematical enabler. What is in it for me, right? I think therefore, that invention might be big from scientific viewpoint, and it might have implications down the road, very long term, decades later, but it may not have any immediate relevance to the end user. Let us keep that distinction in mind, and with that understanding, revisit the rate discussion. So what I am showing in this chart is exponential increase in user transmission rates. It is a linear curve because I draw the vertical axis in log scale. When I was preparing this presentation, I did a speed test. My smartphone was having 75 megabits per second downlink, 17 uplink in May 2022 in the 5G era. And very successfully, generation after generation, this rate increase took place. Can we make a prediction for the future? Well, most likely, before that, what have been the major enablers? Well, these are the 4 canonical enablers. In the physical layer, we have the Shannon theory, which gives us the spectral efficiency, and you multiply that with bandwidth, and then antenna architectures, and then densification. Actually, most of the return came from above physical layer techniques. Well, antennas can also be considered perhaps as a physical layer. MIMO can have big return. Bandwidth, of course, if you have much more bandwidth, much more increase, but in particular densification. So overwhelming majority of this rate increase over decades came through densification. So what will happen next? Probably it will just continue in a similar trend. And what are the foreseeable enablers? Well, that is not difficult to guess either. Probably we will have more advances in physical layers, and then we will have more bandwidth, millimeter wave, terahertz. We will have more and better antennas, and even more densification. So I have reasons to think that this exponential increase will continue at least for a while. But then there is a very unpleasant reality, and that is this exponential increase which has been happening for a number of decades now, is just accepted by public as something that should happen anyway. So it was very interesting and transformative in the early days because it enabled internet, first voice communications and then mobile internet, but not anymore. So all these advances we are talking about, obviously scientifically they are very important. But if I talk about these to the end user again cares about the application. So if it will be just a little bit better FaceTime, it may not be that big of a deal from the end user's viewpoint. Actually, even more than that, NSERC, like NSF, has these transformative research project envelopes. It will be difficult to write a proposal on rate increase because they will not consider that most likely as transformative. Let us make a thought experiment. Here I'm saying something outrageous. Imagine a breakthrough in phi. So spectral efficiency no longer log 2 1 plus SNR. Imagine it is 1 plus SNR square. Obviously, this is truly transformative from a scientific viewpoint. We would be breaking the, how many years now? 80 years old, almost, Shannon theory. However, again, at the end of the day, what does it mean? In the high SNR regime, this is just doubling the rate. So end user, what is the impact? Video streaming, FaceTime, it is just taking place very comfortably today. You really don't need a 2 times rate increase for that. Now, moreover, we have a new enabler in our toolkit now, and that is AI. It is everywhere in my research group as well. But if this AI discussion, model-free way of doing things in communications and networking, if it also boils down to higher rates, then the same question for user, okay, AI, very fancy and everything, but what is in it for me, right? So this has to go beyond the used rate increase somehow. Now, I have to say that AI has big potential in connectivity, but beyond connectivity as well. In particular, smartphone imaging, like sensing and AI applications, can really be transformative. And I will give an example. As many of you know, since last December, I have been having health problems from my eyes. In December, in Toronto airport, while I was waiting my Ottawa connection, in a matter of half an hour, I lost vision on my right side completely. When I went to emergency, doctor after doctor, eye specialist examined me, and each of them was saying, oh my God, you know, so many tears in both eyes. I had 5 laser procedures to stitch them. And actually, those didn't happen overnight. I assume they were unnoticed until one of them hit a blood vessel, and it created hemorrhage, internal bleeding, and that was the reason I lost my vision. And then I don't want to get into this too much, but many worse things were triggered, including retina detachment and then cornea infection, and still it is impacting me big time. And now I am thinking, my smartphone has face recognition. In order to unlock my smartphone, I have to show my face. And how many times I do this? 20 times, 50 times a day. And then, you know, my face every day, many, many times, recorded somewhere, can be recorded. So it would have been amazing if the system alerts me through imaging and AI correlation with my other pictures and databases. And one day I get a notice, Halim, your eyes don't look good, so you should better have them checked. Imagine an application like that. And it is not rocket science. This can happen. We have very high-end cameras today. We can have imaging, other imaging techniques as well. You know, the value of this, it is big. It would have been transformative for many people. A middle-aged person like me can give $100 a month for healthcare applications through this combo smartphone imaging AI. Now, remember, I am paying $80 per month today for everything that this smartphone is bringing. But if you bring me a new good application that has this value to me, I am ready to pay more than everything else, because at the end of the day, it is like insurance, how much money we are paying insurance. The cost of time and effort and everything and the loss of this eye problems to me has been incredible. I would be in a much better side if I were to pay $100 a month for such an application. Anyhow, let me close the parenthesis there. Some more discussion on rate. Rate actually is a three-state machine. It has the good, the bad, and the ugly states. By good, what I mean is reliable high rate. So we have high rate for FaceTime, but the important part is reliable, a very comfortable experience for 10 minutes. And then actually a good chunk of our experience is around sketchy internet. And then in some cases, there is no rate. That is the ugly part. This ugly part is the rural and remote. There is pretty much no infrastructure. And when it is sketchy, doubling the rate really will not help much. And when you have this nice, reliable connection, already high rate, also doubling is no big deal. Let me say a few words. I don't want to get into too much into the satellite part, but since it is in the title, I will have a quick discussion there. Connecting the rural and remote communities to the world through satellites, the mega constellations, is certainly transformative. I don't need to talk about this. The very definition of rural is changing. Rural used to mean, or it means, to be away from infrastructure. But now when you have reliable high rate connectivity, you can have business, you can have education, you can have many things in rural and remote communities as well. And I am humbled to be part of a 7 or 8 person panel commissioned by NRC, National Research Center, Canada, to develop a 150-page report waiting to connect the impact of this connectivity in the rural communities. This is available free of charge. That can be downloaded. And I was, by the way, the only technical person in the panel. The other friends were all from social sciences. Subsequently, with a number of researchers from my group, we wrote this paper, both technical, but also it has human touch as well, or the impact of connectivity and digital divide, the digital divide in Canada, and the role of LEO satellites in bridging the gap. This will appear in the next issue of IEEE Communications magazine. Now, satellite research is obviously very big. As far as I am concerned, the holy grail of satellite research is direct connectivity from LEOs to your smartphone. And when I mean that, I already, IoT applications will likely happen in near future, but what I have in mind is very high rate applications. Here, a remark which is probably obvious to most of you, and that is we have some received power from satellite or HAPS or base station, basically, it doesn't matter. What matters for detection, for reliably detecting zeros and ones in the physical layer is you need sufficient EB over N naught. N naught is fixed once bandwidth is fixed, so you need sufficient EB, bit energy, and that is equal to received power divided by bit rate, meaning that received power can be sufficient, or it can map to a sufficient EB if rate is low. Remember, EB is equal to power received over rate. But if you increase rate, EB will be too low, meaning that if you increase the transmission rate 1,000 times, you will have a deficit of 30 dB in your link budget. Now, why this is holy grail? Because currently satellite community is or looking for million customers. Starlink today, May 2022, number of customers is way lower than the million threshold. I guess the most successful in many ways up and running network, Iridium Next, has, I believe, about 1.5 million customers. But if satellites can reach smartphones directly, then we are talking about a customer pool of billions of users. It is several orders of magnitude business. So it is clear why it is the holy grail. In my group, we have a team, a large team working on satellite networks, another large team, a separate team on HAPS networks. And one of the lines of research in the LEO side is facilitating direct connectivity from LEOs to the end users. So we have industrial partners like MBA. We have we are also in partnership with National Research Center, for instance. I believe Dr. Peng Hu from NRC is with us today. We are working on, again, quite a number of technologies, including inter-satellite laser links. Here I will highlight this direct connection possibility. Well, until recently, until Starlink came up, you would have one or two, or at least at the most, very few satellites in the skies at any given point, and it only makes sense to connect to the one which is right on top of you if it has enough bandwidth. But today, Starlink has more than 2,500 satellites, and that number can increase to 12,000 at some point and even beyond later on. So today, you can see easily a dozen satellites in the horizon, in the skies, sorry, I should say. And future, that number might be several dozens. Therefore, why just connecting to one satellite? You can just send your energy upward, and all the satellite, or many of them, a cluster of them, which can hear you, can all get your signal, and then through RF links or laser inter-satellite links, they push that signal to a cluster head for fusion and further processing. Basically, this is about creating a distributed MIMO. We had our first publication last year in ICC workshops, and Carleton University filed a patent about this invention. We are working on many of the enabling technologies here, how to cluster them, so on and so forth. So it is an important research area in my group. There might be other ways to facilitate direct LEO smartphone connectivity. And at the end of the day, it is all dependent on closing the link. We have link budget, a very simple equation. Received power is equal to transmit power plus gain of the transmit antenna minus path loss plus gain of the receive antenna. So really there are four things there: transmit antenna, transmit power, gain of the transmit antenna, gain of the receive antenna, and path loss. Path loss is a concern, although it is a line of sight, because satellites are far away in comparison to terrestrial network. And on the device side, obviously, antenna cannot be very large. So then we are left with really two controllable parameters: satellites transmit power and antenna gain. Now, transmit power for satellite can also not be increased easily because there is energy constraint. It is very much power limited. Obviously, the satellite is not part of the power grid. Then what you can bet on is antennas, putting up extremely powerful antennas at satellites. And this company, AST Space Mobile, is a startup already publicly traded, is I think a company to be watched for in the coming years, because they are precisely betting on that, building gigantic antennas. Now, big antennas with diameter 8 meters, let us say, is possible in geo satellites, but LEO satellites are much smaller. For instance, Starlink LEO is, I believe, like a vehicle, like a sedan. You can't, it's difficult to put a big antenna there, and there are other reasons as well. So this is what you see in the picture: an 8 by 8 meters, 64 meters square array of AST Space Mobile. And the company has plans to build a 30 by 30 meter, that is 900 meters square array. Imagine an array, 4 times bigger at each size. These are some figures of AST Mobile. What they want to do is to be able to create pencil beam antennas from LEO orbit, and probably 600, 700 kilometers. I want to open another parenthesis here, parenthesis within parenthesis. What is happening on the geo side? The state of the art is really Viasat-2. It has been operational for the last few years. It is a 3-satellite constellation in the geo orbit, and each satellite can have an aggregate 260 gigabits per second from a very high number of spot beams. Obviously, spot beams are very important enablers for satellite networks when satellites move from broadcasting to internet delivery. Spot beam antennas through reuse has been the key. What is state of the art in the geo is, for instance, this Viasat-3, which will be launched in about a year, and this will have 1 terabits per second capacity across, I believe, around 1,000 spot beams. The company already has plans to develop Viasat-4. There is no timeline, but looking the difference between Viasat-2 and 3, this might be late 2020s, maybe 2030. And the company very recently is starting a concept study about Viasat-5, which might deliver around or up to 15 terabits per second from a single satellite. There is a mistype here. It is not 3035, but 2035. Now, let us close that parenthesis and come back to our rate discussion. This sketchy part is very important. Actually, today, we are talking about, well, we are having 5G. My phone is a 5G phone, and 6G discussions are happening everywhere with gigabit per second connectivity to the smartphone as a target. But there is a big but there. All of those are if you are in this state. So with 6G, even with 5G, you can do a lot if you are in this third state in which you have reliable high-rate internet. Imagine, for instance, you are driving from in Ottawa area, Canada to downtown, and having FaceTime in that 15-minute drive. Well, it would not be necessarily a very good experience because it will be on, off, it will freeze, things of that sort. So this sketchy is most of our experience. Again, when we say about 5G, 6G, all these fancy applications, first you have to be in a location where that type of connectivity is possible, and then the discussion goes from there. This sketchy connectivity is I'm not talking about rural and remote. This can very well happen in urban and suburban areas. Today it is on ground, but tomorrow with drone communications and so on, the same situation will be the case in aerial highways. Now, humans are very tolerant for these interruptions in connectivity, but when we are talking about connected and autonomous vehicles or UAVs, robotics type of applications, sensitive applications, you need reliable high data rates everywhere. Now, I know how to bring reliability, as I will allude to in the next slide, or 2 slides later, perhaps in a brute force manner, but the goal really is to do this in a sustainable manner. Now, today, what we are doing is putting more and more terrestrial infrastructure. Base stations everywhere, macros and small base stations, so that statistically, wherever you are, you should be close to a base station. You should have a reliable low path loss, which results in sufficiently high received power in a reliable manner. The key in today's design is over-engineering, over-provisioning, really meaning worst-case design. Certainly, this results in high capex, high opex. Every other industry is being very vigilant about carbon footprint, and the carbon footprint is actually decreasing in other sectors. I don't need to mention electric cars. If you buy a fridge today, its energy efficiency is much better in comparison to a fridge 10 years ago. The exception is the ICT industry. Today, it is still not very much talked about because automotive industry and many other industries contribute more to the carbon footprint. But in 10, 20 years, when those industries did their job or would have done their job and ICT's footprint is getting bigger and bigger, this will be very visible. And it is not easy to do something overnight. So the question is, can I come up with an architecture, an infrastructure which is green and sustainable, in addition to being dynamic and agile? Now, there is a very important remark here. I have been talking about pouring in or putting up in a non-intelligent manner radio access points, but with the advent of AI, we are now talking about putting deep learning everywhere, every edge node. But remember, deep learning is very energy hungry. So it is helping in certain ways or supposed to help, but ICT's footprint will further increase with AI everywhere paradigm, which is not good when it comes to, once again, sustainability. So one idea is to prevent the waste of resources, and that is sectoring. Actually, this has been the case in cellular networks from 1G to 2G and so on. We started with omni base station antennas, then 3 sectors, 6 sectors. And this picture is showing, this is an old picture, Communication Research Center's Milton project, which ran from mid-90s to late 2000s. They had a proposal of a 24-beam rosette antennas. The downside is, of course, when you have a very high number of sectors, is that when there is mobility, there is a big number of handoffs, which is not desirable. Therefore, this was predominantly proposed for fixed broadband access in suburban and rural communities. I guess the idea is clear in sectoring. So you have one cell site with 3 cells, if we are talking about 3 sectors, because each beam is a sector. The term sector became synonymous with cell when we moved to LTE from 3G to 4G. If you have 6 sectors, you have shared equipment of 6 base stations at the same site. But again, this doesn't scale well due to the reasons we discussed. Later, we had 3D MIMO, which is much more flexible than the old sectoring ideas, and with very high number of antennas. At least conceptually, you can go to terahertz if there is a lot of bandwidth as well. But especially in those high bandwidths, millimeter wave or lower end of terahertz like D band, these beams become extremely vulnerable for blockage. They need line of sight. So you might have a terabits per second huge antenna array, very capable, but once it is buried within the city cluster, its coverage region is very small. So even if I give you infinite capacity here, just a thought experiment, it can only give coverage to a very small antenna. And we are going back to the old problem. If you want to cover everywhere with high rate, you have to put very, very, very many of them. And many of them, many of the times, will be underutilized. And here comes our HAPS paradigm. You can have hundreds, even thousands of dynamic spot beams from stratosphere from 20 kilometers. Look at this very nice picture. This is, let us say, a concert, perhaps in the middle of nowhere at a park in a suburban area, which is pretty much vacant most of the year. But that one night, there is a big concert with 10,000 people. How would you give smart, intelligent coverage while your HAPS from stratosphere can help? Yes, HAPS is in the skies once again, but it is not that far away. In my previous presentations, I made some back-of-the-envelope calculations for HAPS capacity. One might achieve even 100 terabits per second in the 7G era, again, based on some rough calculations. And the good thing is that this capacity is centralized at a HAPS or across a cluster of HAPS, and they are provided whenever it is needed, wherever needed. When the demands end, your spot beam is turned off, it is helping somewhere else. In the next few slides, which are important, I will highlight the salient features of HAPS nodes. And I can think of 3 very important features. HAPS has a large surface area This will be important in energy collection. The upper part of the HAPS might be all for, they might be solar cells. And then the lower part can hold a large array, either reconfigurable intelligent surface or antenna array. Since HAPS can be big, its payload can be very heavy as well. For instance, Airbus's Strotobus concept today has a lift capacity of about 0.5 ton. And I assume as we move forward, that can become a ton and tons of equipment. You can put a lot of radio and computing equipment there. Moreover, HAPS has a bird's eye line of sight view of a large area, a metro area, and with that, we can do a lot of things. I will not talk about them today. Again, please refer to my other presentations in my YouTube channel. But a few highlights now. This shared resources is very important in sustainability, in preventing waste. It is not only Node B equipment or antennas, that is electronics, but we can also share photonics, we can share intelligent surfaces, we can share AI, edge intelligence, and so on, storage, you name it. And one-shot operations also brings a lot of opportunities. We have highlighted this extensively in the 2 magazine papers, actually 3 of them, with the most recent one under review. This aerial, a constellation of HAPS on top of highways to facilitate both UAV traffic and ground traffic without need for handoff for very extended periods. This big brother, big sister watching from the sky has advantages in navigation, positioning, localization, federated learning, surveillance, digital twins, and so on. Imagine you are trying to build the digital twin of the city. And by the way, digital twin may come in different granularity. Let us say this is for just vehicle traffic control of a large city, rather than relying on 1,000 cameras on the ground. Basically, the digital twin can construct it from the shared cameras at the HAPS with gigapixel cameras. You can identify each individual on the ground. Imagine a day, no one will be lost. Your elderly family members with, let us say, dementia, if they are lost, just they can be found, located through HAPS. Once again, applications are limited with our imaginations. And once again, this framework results in a sustainable architecture and infrastructure. We have a lot of research under sustainability just going on, and hopefully will be available in the literature later this year and in 2023 as well. I will today talk about only one line of research in the remaining 10 minutes. So at the moment at Carleton, these are the areas either we conduct research with our collaborators as well, or we want to do research from access to backhauling to interference management, antenna architectures, edge intelligence, studies at different spectrum. We don't do propagation studies, but we rely on propagation studies, sensing work, navigation, localization, positioning, control and management. We would like to get into cybersecurity, which is extremely important. none of the fancy applications we are talking about will be adopted unless security issue is sorted out. And HAPS being a hyper platform with tremendous opportunity, it might become a tremendous concern or threat if it is compromised. Therefore, cybersecurity is very important. Your entire network can be jeopardized. As I mentioned, sustainability and emerging technologies in conjunction with HAPS, and today I will highlight risks. By the way, these are ICT topics. There are many other very important, at least as important as ICT topics, non-ICT topics for HAPS concept to take off. For instance, energy budget. We started working on the energy budget, and more work will continue in the coming years. Now, HAPS is an important topic from architecture viewpoint. Risk is a very important topic. It goes without saying. How about combining the two beyond being opportunistic? I'm not here saying that, hey, this is hot, let us just combine them. More than that, there is can there be a synergy here? And the synergy is the large area of HAPS and the fact that HAPS is energy limited. So if you can put a gigantic antenna array at HAPS, and by the way, we are doing research in that direction as well, one has to be aware of the fact that that will consume a lot of energy. Under the premise that RIS construct consumes much less energy, it sounds an interesting alternative. And the fact that RIS has a very large, it can have a very large surface area, can we just put a gigantic RIS on the below side of an airship? Just to give a dimension, I believe Airbus's Stratobus concept has a length of 140 meters. So that is a lot of surface. In my research group, a PhD student, Safwan El-Fattani, along with answer PDF Wael Jafar, with a visiting researcher, Dr. Yassin Hamamoch, they did an initial study with our collaborators at Huawei, Nokdao and Pei Ju. We did an initial study. By the way, I must mention that all these are very exploratory. As I wrote here, it is a long shot because RIS is not there yet in even small scale in terrestrial networks. There is a lot of pilot projects, pilot implementations, but it is not part of the terrestrial network. HAPS, lots of studies, but it is not part of the network. And now I am trying to put these two components. Therefore, it is long shot, but it is, let us see if it is worth investigating this further. So in this study, we checked as a first order investigation, the feasibility of intelligent surfaces at UAVs at an altitude of about 100 meters, then at HAPS, 20 kilometers, as well as at LEOs, 500 kilometers. And these initial studies has shown that, without getting too much into detail, but please refer to the paper if you are interested, HAPS seems to be a good compromise. Now, a very important point here, when we have RIS, we have a product channel. So when we calculate the path loss, it is the product of uplink and downlink, which becomes a huge path loss. In order to compensate for this tremendous path loss, you need a large surface. Now, in the case of satellites, perhaps you can put still large surfaces at the satellite level, but the distances we found on the too high side. So the path loss, product path loss becomes, in at least some cases, prohibitive. Path loss is very manageable when it comes to UAVs at 100 meters above the ground, but UAV has very small surface area. And then there are other issues, vibration and so on. So HAPS is a good middle ground. That was the message from the concept paper. Later last year, we came up with a very detailed 3GPP compliant link budget analysis, which got published in ComSAC's Open Journal of Communication Society. Now, another remark. Actually, I find it very interesting, almost unbelievable. There is nothing new under the sun, as they say. It turns out that back in late 1950s, you know, this is 70 years ago, there was a joint program between NASA and Bell Labs about putting a passive reflector in orbit. So this is at, well, between LEO and MEO orbit with today's standards, 1,600 kilometers. Quite a large 30-meter diameter, totally passive metallic sphere, and it was put in orbit back in August 1960. And once again, I find it terrific that by late 1960s, there was already a constellation, 46 of them, orbiting around the globe at 4,000 kilometers. It is a MEO altitude. Then, you know, it is a forgotten history because I think more advanced satellites came up and there was perhaps no need for these dumb reflectors. Interestingly, after 70 years, we are revisiting the concept, but now with much more advanced enablers with an reconfigurable intelligent surface at a HAPS at 20 kilometers. It is not 4,000 kilometers. Now, some basics. When I draw SNR CDF for a terrestrial network, often it exhibits itself in a form of a stretched S, meaning that there will be high-end users observing or experiencing extremely high rates because they are very close to the small base station, let us say unobstructed, 50 meters, 20 meters away. But especially in those high frequencies, which small cells are constructed, since propagation is very vulnerable with respect to blockage, there is a very bad low end of the tail as well, which results in very low rates. Now, if I intensify the deployment, so densify what I meant, obviously the rate CDF will be better, but this is not what I want because it is not good for sustainability. On the other hand, HAPS CDF is very different. This is a bit of an exaggerated graph just to make a point. HAPS, if it has a small footprint, let us say intentionally, as a hotspot, whether you are 20 kilometers below or 20 kilometers and a few hundred meters this way, it will still make 20 kilometers. So if users are in a small, rather small footprint in line of sight situation, path loss is same. So all of them have the same SNR, same spectral efficiency and then rate with equal resource assignment. So what does this mean? It means that if a terrestrial user has a very good connection, a very good view to a small cell, let those users be connected to the small cell, because as a base station 50 kilometers away, 50 meters away, obviously will give you much more received power than HAPS at 20 kilometers. On the other hand, those users in the lower tail, they can be connected to HAPS. This will be a very rudimentary radio resource management and connection scheme. You can write your questions in the chat box. We will have a discussion at the very end. Now, this figure is kind of something straightforward, but it is developed with attention, and it is making a very important point. First of all, I have 10 by 10 kilometer area. So this is, let us say, a good region of Ottawa. And 100 users here shown by circles. And then in this picture, there are 4 base stations shown by triangles. By the way, the propagation studies are done according to the most advanced 3GPP documents in very much detail. You can actually check if you wish so. This is a release 17 document. But let me go back to my figure. Here, the key issue is that if we have a threshold spectral efficiency for outage, and in this figure we used 1 bits per second per hertz with, I believe, 2 megahertz of bandwidth. And here it is only based on the link quality. There will be, due to the shadowing and distance, users which are around access points will have good links, meaning that spectral efficiency is above threshold. Therefore, they are connected to the terrestrial base station, as you see, so the green ones. But there will always be cell edge users. As you see, very nice. It's a statistical picture, but cell edge users also visually show themselves. They don't have, this user, for instance, does not have a spectral efficiency as high as 1 bits per second per hertz to neither of the 4 base stations. Therefore, it can be absorbed by HAPS. Using the very same study, what we are showing in this figure is how many base stations you will need for a given outage or connectivity level at different carrier frequencies. So it starts with 900 megahertz and then ends with a millimeter wave at 30 gigahertz. Here, congestion is not taken into account. It is only link quality. As expected, despite shadowing, at lower end 900 megahertz, legacy cellular frequencies, low bands, if you are, for instance, targeting 5% outage, that is 95% connectivity, you can get by, say, around 4 base stations in a large area of 100 kilometers square. But if the carrier is 2 gigahertz, now let us say 4 will not cut it, you need 8. If you go to millimeter wave, 20 gigahertz, 30 gigahertz, at 95% coverage in this region, you actually need hundreds of base stations. I don't know where this curve cut 95 percentile. So that is something we knew already, but it also quantifies this picture with some real 3GPP compliant studies. So we have actually come up with a new construct. This is a sequel in this HAPS-RIS synergy studies. And just about 10 days ago, this paper is submitted to GlobeCom 2022, co-authored by Safwan El-Fattani with Dr. Animesh Yadav. We have a large metro area, 10 by 10, 100 kilometers square, and there are a number of terrestrial macro base stations. This figure shows 2, but in reality, the number will be very high, and actually that number will be a variable in the study. Many users, or maybe overwhelming majority of the users, if the network is dense, will have direct connectivity to the macro base station. But occasionally, there will be users like this one, in particular due to shadowing. It will not have a good link to neither this base station nor that base station. And congestion, as the number of users increase, will make this situation worse. So all the users in the entire network, which cannot connect to the terrestrial network, their signals are rerouted to a control station. This is like a ground station in the satellite terminology. So their signal goes to a HAPS and then come back to the user. It is really important to emphasize that this user here cannot connect to to macro base station. And let us consider downlink here. It is not that this base station now shoots this user signal to the HAPS. That is not a good design. At the very least, this base station will require extra hardware, new set of antennas towards the HAPS system. Rather, all that hardware is shared at the control station. And if I give an example from Ottawa, this might be a user downtown, and this ground station might be in Canada, for instance. So once again, all those users in high data rate outage, their signal goes to HAPS, and then from HAPS come back to the user of interest. As we mentioned before, closing the link in link budget is the major concern. So in this study, we didn't take interference into account intentionally, so that should be kept in mind, maybe as a future study for Safwan, and I believe he is doing that as the next work in the sequel. But here, once again, the question is, can I close the link under the concern that there is a product path loss, but under the hope that I can put a very large array here? Now, this study, in addition to the mentioned 3GPP document in the earlier slide, also use for HAPS and satellite connectivity a 3GPP study called Study on New Radio to Support NTN. And a big advantage of this design is that the ground station or control station can have a much higher EIRP, more than 30 dB, 33 dB higher in comparison to ground-based stations. How come? Well, a little bit more transmit power, but mainly due to very large antennas. In a downtown base station, you can't put, say, 8-meter diameter dish, but in a ground station, you can put that as at a convenient location, and that additional, well, at least today, 3GPP allows 30 dB more antenna gain. Tomorrow, it might be even 40 dB, and it will come as an advantage for the HAPS link. Now, let us continue. I will motivate the quantitative discussions through this curve in the paper under review. Remember, in this study at least, the threshold for connecting to a ground-based station was set at 1 bits per second per hertz, and the bandwidth was 2 megahertz. So the users which have hardly enough power for the base station, terrestrial base station, will have 2 megabits per second link. Users which are much closer to terrestrial base station will have better links, but this figure is for the worst case user. Here on the vertical axis, I am showing, or we are showing, the worst user data rate. On the horizontal axis, the number of reflectors at HAPS. Since this thick black line is terrestrially connected users, regardless of what is happening in HAPS, the worst case users have 2 megabits per second connectivity. But the worst case rate at HAPS will depend on the number of reflectors at HAPS. And as you see, as that number increases, we can have a worst case performance much better than the terrestrial network. And here again, the devil is in detail, as they say. I do not have any interference concern. So HAPS has enough bandwidth, and here it is a little bit different than the earlier part of my talk where I mentioned the harmonized spectrum. Here I am assuming that just not to deal with interference at the moment, HAPS has a separate dedicated spectrum, and a lot of bandwidth congestion is also no issue. So only from link budget viewpoint, I see that this is doable at the expense of putting a lot of reflectors. So this curve or this figure starts from 200,000 reflectors. It goes up to 600,000 reflectors. Now, some of you might say, oh my God, 200,000 reflectors. Let us see how big that is. The size of a reflector in the literature generally is taken about 10% to 20% of a wavelength at each side. So here we took a more pessimistic number, 0.2 by 0.2 lambda. And at 2 gigahertz, this paper, the study was made for 2 gigahertz. At 2 gigahertz, a wavelength is, or at least here, anyhow, now I actually I have just confused myself. Just let me do a quick calculation on the fly. 3 10 to the 8 divided by 2 10 to the 9. It makes 0.15. So this 0.15 is actually the size of one wavelength. So if you multiply the 2, it makes this much. But I'm not sure if I integrated 0.2 in my calculation. Just give me a very quick second here. I hope I didn't make a mistake here. So 0.2, sorry, 0.0225 times 200,000. Yeah, actually, you know, I'm thinking that I probably forgot to integrate 0.2 in my calculation. So without that 0.2, it becomes a large area, 200,000 of them. And if I think that as a square grid, it makes a 67 meter by 67 meters, a huge surface. But I was about to say that, you know, given that today AST Space Mobile is thinking about a 30 meter by 30 meter antenna array, it may be possible to have such a RIS just a little bit bigger than what is considered today. But now I'm thinking that this has to be multiplied by 0.04, which makes a much smaller area, because I think I forgot in the calculation this 0.2 coefficient. And even if this is bigger, at higher frequencies, obviously the size, even 200,000 of them, becomes much more manageable. Obviously, this is not an indication directly in this study, because at 30 gigahertz, the path loss will be much higher. So you would need a much higher number of reflectors. I guess, Safwan, in your ongoing work, you should repeat the very same study at 30 gigahertz as well, one low band, and one in millimeter wave, and then do the size calculations. Now, 200,000 reflectors. Yes, Safwan, sorry, please go ahead.
Yeah, I think you forgot to, as you mentioned, to multiply by 0.2. Right. So the size, instead of 65 by 65, it becomes the total is 180 square meters.
Yeah, actually, just let me phone by. Yes, I am sorry for that. That is, I guess, 4,500 times 0.04. That is right, 180 meters square, which is just like 14 by 14, right? Something like that, or 13 by 13, or sorry. So 180, take square root of that.
13.
Yes, 13 by 13. What is that?
Yes, 13.4, something like that.
Yes, much more manageable. My apologies for that mistake. Anyhow, so clearly this may be doable. We have to investigate the control or scalability of managing this many reflectors, including channel state information. However, given that we have a line of sight link, and channels from one reflector to another may be highly correlated, and this might make CSI calculation even feasible. And another, I guess, one point we should not miss is that this 200,000 reflectors is not for one user. This is for a pool of users in my study, red ones, which cannot be connected to the terrestrial network. And why I am bringing up this study in the context of sustainability? Well, because the alternative is to put a very high number of smaller risks on the ground. Take 200,000. So maybe 50 of them at 4,000 elements each, I have to put strategically in my 10 by 10 network. But how much strategic it can be? This is a static deployment. Again, here comes the shared usage in the HAPS. And actually in the HAPS, I can allocate more surface, less surface to an individual user. Once you put these surfaces on the ground, they are not dynamic, they are static. So very similar to base station, as well as AI centralization to prevent waste, this HAPS risk paradigm also may result in a much better overall performance in a large area for risk paradigm due to the shared resources. basically, that is really, I want to just leave that discussion there. If you are interested, please look at Safan's work. We can send the Globecom paper as well under review. And here is my final thoughts. I have a very simple thought. Why it is that surprising or unbelievable to put a new infrastructure layer in stratosphere? You know, if we were having this discussion without satellites, so only terrestrial network. So let us assume another thought experiment. Satellites never existed. Starlink is not there. Then someone might say, this is quite a big leap, right? We have the terrestrial network, and now you are talking about another layer. Well, another layer at 500 kilometers or between 500 and 1,000 kilometers is already happening with a lot of other challenges due to orbiting and otherwise. So if it is happening, why not? What is so surprising, puzzling about having this new network infrastructure between ground and space layers? I think this is doable. We are looking for both inventors and entrepreneurs, and maybe at some point entrepreneurs like Bezos and Musk will also put big bucks in this type of initiatives. In the beginning, I show some vision and position papers from last year, but we have many very recent papers here. I'm not even showing the papers between the past and recent. Many works, Rosetta Shafi, we are doing a myeloma work with her. There is a very recent paper in early access with Shishi Ren and Omid Abbasi, caching and computational offloading in high altitude platform assistant intelligent transportation systems. And in this sequel, another paper will soon be submitted investigating actually handoff statistics in HAPS facilitated or HAPS assistant intelligent transportation systems, and many other works as well. By the way, in our group, we also have quite a bit of work in UAV communications and networks. And if you are interested, please go to my website. All our publications are available there. I already mentioned the YouTube channel. Okay, so this concludes my talk, almost 2 hours. I will just stop sharing. Yes, I stopped sharing now. We do not have, unfortunately, much time for a discussion. Since most people here are researchers from my research group, I suggest that we carry on with the discussion offline. But I see some guests here outside my group. If they have any questions, I will be more than happy to take them in the next few minutes. Any remarks, questions? Okay then. Well, let me stop sharing. This presentation will be available in my YouTube channel. Let me stop recording. Thank you very much. And we will continue with these meetings in the coming months.